All right, so remember the writer from number 1 and 2, example 1 and 2, that guy? That guy. Well, that guy is, he leaves the fair, he goes home and he constructs a perpetual motion machine. What does that look like? Well, his looks like this, okay? Yeah, he suspended a weight from a spring above the ground. He made this little contraption, this gallows kind of looking thing. And the weight is attached to the long spring and he bounces it up and down. As it bounces, its distance from the floor varies, thank you, sinusoidally with time. The rider sets the spring in motion by compressing it to a high point of 60 centimeters above the floor, and then he starts his stopwatch. So how do you get this thing going? You can either pull it down and let it go, right? Or you can compress it and let it go, and that's what he did, okay? So first of all, we have to understand that what we're actually measuring. In this case, we are measuring the height of the weight, the bottom of the weight, in centimeters above the floor, okay? And it says here that after he starts his stopwatch, when it's 60 centimeters above the floor, 1.8 seconds later, it gets its closest to the floor, which is 40 centimeters above it. Sketch the graph of the function. So you can kind of imagine that the high point right here is going to be, let me use a different color. The high point is going to be 60 and the low point is going to be 40. That kind of already gives you the range of your function, right? So you can kind of see the dotted line graph there. It's going to essentially do something like this. Yep. As you imagine, it's tracing out, you know, something in time. So let's go ahead and sketch our graph. Very good. Before we sketch our graph, we're going to need to collect our information. So just like we've always done, let's come over here and collect our A, B, C, D, P, and R. All right. And since we already know the range is going to be from 40 centimeters at a low to 60 centimeters at a high. Okay. Now, once we know the range, we can figure out two things, can't we? Because of the symmetry. The first thing that I might look at is what would be the equilibrium. Like before he put this thing in motion and the weight was just resting, what would be the equilibrium? 50, right? It's going to be the midpoint of the high and low. So 60 plus 40 is 100, divided by 2, you get 50. That's going to end up being not just the equilibrium, but what letter in our equation? D, good. So D is positive 50. We have a sinusoidal axis at y equals 50, if you want to write like that as well. And now that we know the sinusoidal axis, as Brady already said, we can figure out the wave height. What is the wave height? Yeah, from 50 to the high point is 10. From 50 to the low point is 10. So it's also half of the distance between the high and low, if you wanted to do it that way. So it's 10. Cool. All right. Now, remember, the C is always going to depend on whether we use sine or cosine. So the other two that we need are the B and the P. Those are related to each other. So from the graph or from the description, we're typically going to get the period. What is the period? Is there any information up there that'll help us with that? 1.8 seconds to get from a high point to a low point. Is that the period then? No, the period is how long it would take then to return to some similar point. In this case, the high point.
So 3/4 of the way.
Not 3/4. It's a half. 1.8 is half.
Oh wait, that's half.
So it's a half, right? So 1.8 is a half of a period. High axis, low. So the period should be twice that. Okay, so the period should be 3.6 seconds. Okay, and now that we have 3.6, we can find B, because B, remember, is 2 pi over P. So 2 pi over 3.6. If we simplify that, that's the same as pi over 1.8. Now look at that right there. Say it with me. Yucky, yucky, gross, gross. Yucky, yucky, gross, gross. Okay, here's why it's yucky, yucky, gross, gross. We have two different ways of expressing parts of numbers in that one little expression. We have a fraction and a decimal. That's mixed notation. That's like speaking to someone in two languages at one time. Okay. Pick a language, pick a notation and go with it. So I'm not going to have answer choices that would have mixed notation. So let's go ahead and convert this to a nice fraction. Wow. Okay. That's what I was getting at. Right. So let's come off to the side here to our workbench somewhere and look at 1.8. 1.8, we read that as 1 and 8/10. Yes. That's another way to read it. 1 and 8/10, which is the same as 18/10, which is the same as what Brady said, 9/5, right? So 1.8 is 9/5. Now, if we do pi divided by 9/5, that's a complex fraction. That's also yucky, yucky, gross, gross. So now we state change flip and we get what? 5 pi ninths. And boy, isn't that a lot better looking? Yeah, yeah, I like that. So pi over 1.8 is the same as 5 pi ninths. Más mejor que bueno, we say. Speaking of two different languages. More better than good. All right. So I think we're ready for our graph, aren't we? Yeah. Okay. So let's go ahead and do that. I'm going to give myself a y-axis. Y-axis. And then the x-axis I can put relatively low because we're measuring the distance above the ground and never goes negative and never goes below the ground. So we can get our vertical axis in order. Now, you could just call this the low point of 40 and this the high point of 60, and then come right there in the middle and put 50. Now, is it to scale from 0 to 40 as it is from 40 to 50? No. So sometimes you might see these little marks on an axis, like down towards the bottom, like two little marks like that. Y'all know what that means? That means that it's kind of like cut out. Like we're not, in other words, I'm not drawing it to scale from here to here is not the same from here to here. So you don't have to do that. The y-axis, I'm not as concerned about. The x-axis is, because we have to run through a continuum. So if you want to do that, that's fine. If you want to put the two little lines there to show a break in the graph, you can. But I'm going to go ahead and draw in my sinusoidal axis. Now, the other thing that I'm going to do, since this is a word problem, is I'm going to label the axes. I'm going to call this h of t for height above ground. And then I'm going to put the units next to it, centimeters. Okay. So I've defined the function to be h instead of just y equals. All right. Now the x-axis, this is where we want to be a little bit more careful. I tell you that it starts at t equals 0, which is right here, by compressing it to 60. So that's going to be a high point, isn't it? So that's pretty nice. So I don't have to make a sacrificial axis. It's all about getting your values on the x-axis nicely. So if I know 1.8 is a half of a cycle, I'm going to just come over here, right about here, and I'm just going to call that 1.8. That's half of a cycle. And I know that's where it's low. So I can put a low point there if I want. But I need to label something in between, right? 1.8 is a half of a cycle. I need my quarter cycle. So now I'm going to bisect that. And remember, 0 is also a critical value. So what's half of 1.8? 0.9. And 0, remember, is still a critical value. So now what we need to do is try to make sure, since I have two critical values shown, I need to make sure that the distance between every other subsequent critical value is roughly the same. Okay. So now I'm just going to add some marks here. Add a mark, another mark, and what the heck, one more. And then I always want you to have one negative value. Now, in this case, the negative value doesn't really make sense because he started his stopwatch at 0. But had this thing already been in motion, going backwards in time is not impossible. You're basically extrapolating backwards to something that was happening before you arrived, right? And now we just keep counting by 0.9, okay? So I'm going to go backwards to negative 0.9 first. And now I just keep adding 0.9. So what's 1.8 plus 0.9? 2.7, good. Plus 0.9, 3.6, good. Plus 0.9, 4.5, plus 0.9, 5.4. Nice. Okay. You need at least 5 critical values for one cycle, and you need at least one that's negative. So that's enough. All right. Now I'm going to put T over here, and I'm going to put seconds. Okay. We want to label the graph. Now, this is again why we need radians. Radians are unitless, as are the sine and cosine ratios. They're unitless. And because we have unitless X and Y axes, we can assign our own units to them, right? If we were measuring in degrees, we wouldn't be able to put time on the X axis. Okay, so that's important. All right, so as long as we have a high point or a low point or an axis point and we know where it's going, we have the rest of the dots. So I know at 0.9, it's going to be right here. And now I'll just put the rest of the dots. From 1.8 now, going to the right, I'm on the axis at 2.7. I'm high again at 3.6. And then I'm on the axis at 4.5. I'm low at 5.4. And that's as far as I went. And then I'm going to come backwards once. And I'm on the axis at negative 0.9. All right, now you just connect the dots with your exaggerated frowns and exaggerated smiles. Make sure that the curvature changes on these sinusoidal axis points. Remember, what do we call those values where the curvature changes? Inflection points, good. Okay, the curvature changes concave down like a frown to concave up like a cup or like a smile. And then past the last one, just turn the corner and draw a little arrow. Turn the corner, draw a little arrow, show that it does keep going. All right, so that wasn't too bad, right? That wasn't too bad at all. Once we have the graph, now we write the equation, okay? So that takes care of part A. Find the particular equation for the distance from the floor in centimeters as a function of time. So that's part B. So here's part B. I'm calling my function h of t. You could call it d of t for distance from the floor if you want. And let's see, I can choose whichever function I want, sine or cosine, and I can use a positive or a negative value of a, doesn't matter. But what would be the easiest function to write that would not require a phase shift? Cosine, right? If 0 is ever a critical value, and it is here, you can write whatever function that is at 0 without a phase shift. So let's do that. Because up here is a high point at 0, we'll use a positive cosine. That's a positive cosine. So what was our amplitude? It was positive 10 cosine of parentheses b, which is 5 pi ninths, times t, close parentheses. We don't need a phase shift. And then we just need to say plus 50. All right, so there's one of them. Now, what I'll probably have you do on the test as well is write another one. And at least one of the two has to be in terms of sine and cosine, and at least one of the two has to have a negative value of a. So with those criteria, if I've already written a positive cosine, I would then need to write a negative sine. So let's just do that. Or we'll say h of t could equal, now for a negative sine, that would be a negative 10 with a sine. And now I'm going to have extra parentheses because I will have a phase shift. 5 pi ninths, open parentheses t, plus or minus something, close, plus 50. What's the first value, the t, that I can get over to for a negative sign? 0.9, good. Negative sign would be on an axis going down. And at 0.9, we're on an axis going down. So that would be t plus or minus 0.9. Minus, good, it's the opposite. So either one of these equations will give you that graph above. And of course, there's infinitely many more. Now, here's what we do. Okay, so you're on the test, you've written your equation. You only have to use one of them. Okay, but I'm going to have you write two of them. Let's make sure that we've got everything correct so far. So now we go to the calculator, turn it on. What's up, calculator? Go to y equals. First of all, go to mode. What mode should we be in? We should be in radian mode. Make sure you are. Now go to y equals. Let's type in the first one here. 10 cosine of alpha y equals, right? 5 pi divided by 9. Go to the right. We're going to use x on our calculator instead of t. Close plus 50. Now, don't just hit graph. Don't just hit graph. It's not going to be meaningful. And don't just hit zoom 6. Do we already know a nice window in which we should have our graph? Boy, it's right there in front of us. So now you graph it in your window. So let's go to window and use the x min, x max for your t min, t max. I went from negative 0.9 all the way up to 5.4. So that's what I'm going to put my x min, x max. And then for the x scale, if you want to put 0.9, you can, or you could just leave it alone or turn it off to 0. That's not really that important. Now your y min, y max, this is where you want to put a little bit of a buffer, because remember your calculator uses the top and bottom of the screen for words. So I'm going to go like from negative 10 instead of 0, and above 60, I'll probably go to like 80. Okay, and then I'm just going to turn my y scale off by putting a 0. I don't want to have tick marks on the axis. It's not that important to me. Now, when I hit graph, I should see what I've already graphed by hand. Yes? If not, you've typed it in wrong, or maybe you're in degree mode. You don't want to answer questions, though, until you can verify what you've already done. How's it looking? It looks really good, right? Now I know how awesome I am, or I'm confirming how awesome I am. The calculator's telling me how awesome I am. Now I can comfortably answer the questions by using the equation. And if you want, you could go ahead and sketch the second equation that you did, and it'll trace right over it. Okay. I'm not going to do that, but you certainly could. All right. So I'm using this equation for the rest of my questions. All right. So pausing my calculator, we did part B. Part B is over. Boom. Now that we've got our equation, now we can start using it. Here we go. Part C, what is the distance from the floor when the stopwatch reads 10.5? At this time, is the weight moving away from the floor or towards the floor? Well, if I go back to my graph and just hit trace and type in 10.5, I'm going to get an error. Why? My window doesn't go that far. I only went to 5.4. So you have two options, right? You can go back to your window and set your X max to something that includes that number, which I'm not a big fan of doing that. Or you can go to your home screen, right? Let's do that. Second, quit, get out of there. So here's what you have to write on part C. How do you communicate to me on a test that you are plugging in a 10.5 for T into your function H? What do you have to write? H of 10.5. That's all you have to show me. Okay, and then you can go straight to your calculator. So how do we recall it from the home screen? Remember, alpha trace gets you to your shortcuts. We have our equation in Y1. I'm going to open parentheses and I'm going to put 10.5 close parentheses, and there it is. So it's 58.660 centimeters. Here's the other thing. You want to put units on all your final numeric answers. Okay. Now, how do I know at that moment, since I don't have the graph, it's not blinking, I can't see it. How do I know if it's moving up away from the floor or down towards the floor at that moment? Yeah. Very good. Yeah, this is just another option. So hit alpha trace again, and you can type in a value that is a split second after that. So I say like a tenth would be good. So where is it a tenth of a second later? It's water higher, right? So we can say 58.660 centimeters moving. Yeah, going up would be fine. Going up. Or you could say moving away from the floor, right? They mean the same thing. Going up. Okay, I think, did we answer all of part C? Yeah, we did. Okay, part D, party. Hey, it's party. What is the first positive value of time where the weight is 47 centimeters above the floor? What is the first positive value of time where the weight is 47 above the floor? Did it say 47 above the floor going up or going down, or does it matter? Doesn't matter. So yeah, positive value of time, right? So here's what we're going to show on part D. I'm going to put h of t equals what? 47, right? 47. And now we're going to go back to y equals, and in y2, I'm going to graph 47. And it should graph as a horizontal line. Boom. And now all you got to do is look for the correct point of intersection. If I had said, where is it at 47 going down for the first time? That would be the very first positive one. That's the one we want. But what if the instruction said, where is it 47 going up for the first time? It would be the second point of intersection, right? Or if I said, where is it at 47 going down for the second time? That would be now the third point of intersection. So don't always just assume that you're looking for the very first positive point of intersection. You have to read carefully. But that's what we're doing in this case. So now we go second trace number what? 5. Is that your first curve? Look at it, say, yep, hit enter. It should put you on the horizontal line. Is this your second curve? It's not really a curve, but yeah, whatever, calculator, hit enter. And now for your guess, you just scroll over closer to the one that you want. This is where you need to get to the correct point of intersection. And there it is. So now underneath h of t equals 47, we put t equals 1.074. And what are the units? It is going down, but again, look at what it said. It just says, what is the first positive value of time when it's at 47? It didn't say 47 going down or 47 going up. I just addressed that in case on the test I do ask something more specific. All right. So 1.074, what would the units be on that? Seconds. Good. SEC, right? Southeast Conference. You can abbreviate. That's fine. Okay. If I felt I needed to use this number again for something else, could I store it? Yeah. Let's just review how to do that. If you're going to store it, since it's already there as X, go to the home screen, second mode, and hit X, stow, and then you can hit like alpha A. Boom. And now it's locked in there as A. X, stow, right above the on, and then alpha A. But and if you're calling it A on your calculator, you can call it capital A on your paper, just as a reminder to yourself. That's fine. But I don't think we're going to have to use that. Just reviewing skills. Okay. A, B, C, D, E comes next. All right. The first E, right? I like to use letters twice, just like on example 1. So the first E, during the first 9 seconds, for how long is the weight at least 43 centimeters above the floor? During the first 9 seconds, for how long is it at least 43 above the floor? How do we do that? I want to know where h of t is 53 or whatter. When it says at least, it means or bigger, right? So you could put h of t is greater than or equal to. I would accept that for your setup, or it's okay if you tell me h of t equals 53. I would accept that as well. So really what we do now is go back to y2, and instead of 47, we just put 53. Now, here's one thing that I'm going to do. I'm going to change my scale. It says during the first 9 seconds. I'm going to go to my window and put my x min to 0 and my x max to 9. You know why I'm doing that? I don't want to be tempted by outside intervals. Now I'm going to hit graph. You could do that. Now, I have 9 exact seconds graphed on my calculator, yes? I want to know for how many seconds is the graph above or below that line? Above, right? Now, you can look at these two right here. Because of the symmetry, if I can find the time that it's above from 1 point going up to 1 point going down, if I find that distance, I could double it to get the next interval, right? But notice there's also this little piece in the beginning where it starts above that, yes? So here's what we're going to do. We're going to find those points of intersection. So I'm going to do this one first, okay? I'm going to say t sub 1 equals and t sub 2 equals. So let's do that. Second trace number 5, second trace number 5, enter, enter. And I'm just gonna choose the first little set. Okay, so right there, that is 2.874 seconds. Now, am I gonna use this value again? I am. So this is where I need to store it as A. So I'm not gonna even store that other one as A. I don't need that. So before I find the next one, go to your home screen and do X stow alpha A. Boom. All right, now it's locked in there and I called it A on my paper. Now I'm going to go back to the graph and I'm going to find the next point. Second trace number 5, enter, enter, scroll over towards this one. And hit enter. Boom. I'm going to write it down to 3 decimals, 4.325 seconds. And now I'm going to store that as B. So go back to your home screen and hit X stow alpha B. Boom, and it'll appear. It overwrote the previous X. All right, now all I need to do, if you go back to your graph, if I can find the distance between those two, I can double it. But I also need to find that point of intersection over there, don't I? That first point of intersection. So let's do that. I'm going to say T sub 3 is equal to second trace number 5. Enter, enter. And now I just scroll with it, baby. You and me just scroll with it, baby. Mm-hmm. Am I close enough? Looks good. Enter. And it's right there, 0.725. And I'm going to store that as C. Okay. So second quit, and I'm going to hit X stow alpha C. Boom. All right. Now that I have all of my points of intersections written down and stored, I need to communicate how I'm going to use them. Okay. So the time that we want T is going to equal B minus A will give me the time it's up above there. And I have to double that. So I'm going to put 2 times B minus A. And then I'm going to add C to it. My handwriting's kind of bad. Looks like my grandmother's handwriting when she had arthritis. Let's try this again. 2 times B minus A plus C. All right. Does everyone see why that works? The 2 times B minus A are these 2 regions here. There's one of them. There's the next one. And then all I have to do is add, since it's the first from 0 to C, I could just add C to it. All right. Now, yeah. C would also be half of B to A. Yeah. 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 It's also B, it's, bless you, it's also B minus the period, B minus 3.6. Okay. But there's a lot of different ways to do this problem. I would just say, go ahead and find it. Let the calculator find the actual value and store it. And then you can just show me how you're using them. And now we just go to the home screen, since I've got them all stored, and we just type it in one time. Here we go. Ready? I'm ready. You ready? Let's do this. 2 times alpha B minus alpha A, close parentheses, plus alpha C. And there is no rounding error. And we get T equals 3.627. And what are the units? Seconds, SEC. And there you go. So during the first 9 seconds, the weight spends 3.627 seconds above 53 centimeters. Okay. So that's similar to that problem with the rider on the Ferris wheel. Less exciting though. All right, so now we finished that E, and now there's one last little piece to go, and it's part E again. E2. Look at this. If the rider's little sister started the machine when the rider was at the yogurt shop. So like, imagine that he set this up in his room and he hadn't put it into motion yet. He was going to celebrate setting it up, and he was going to go to the yogurt shop to celebrate and then come back and start the machine. But while he was gone at the yogurt shop, his little sister came in and started it. And when he got back, it was already in motion. And he was like, you gosh, dang it. But it's perpetual. So now he's not going to stop it. So what is he going to do? He's going to hit start on his stopwatch when it's 51 centimeters above the floor, moving away from the floor. Okay, dang it. We have to figure out what the new equation is going to be. Everything's going to be pretty much the same, except t equals 0 is not going to correspond with 60 anymore, right? T equals 0 has to correspond with 51 moving up, right? And it could be at any 51 moving up. It doesn't have to be at the first or second. So now here's what we're going to do. Here's what we're going to do. We're going to do second part E. We're going to say, okay, where's h of t equal to 51? I'm going to go back to y equals, and now I'm going to graph 51 instead of 53. Now this one, it's very specific. It says it needs to be 51 above the floor, moving away from it. So which point of intersection do we want, the first or the second? The first one is at 51 centimeters moving towards the floor. It's going down. We want it to be 51 going up, right? So we want the second point of intersection. Agreed? Yeah. Or the fourth. You could do the fourth if you want. I mean, there's infinitely many, but let's just do the next one, okay? The second one. So second trace number 5, enter, enter, and we'll scroll over here. There's where it's at 51 going up. Boom. So I'm going to write that down. That is now t equals 2.757 seconds. Now you can round or truncate to 3 decimals. The question is now, what do we do with that number? I need that spot right there where it's blinking. I need that to be the y-axis now. So I need to pick that graph up that I have and move it to the left and set it back down. Does that make sense? Pick that graph up and take the blinking part and move it left so that the blinking part's now on the y-axis. How do I move a graph left in the equation? Do I add that number or subtract it? No, it's opposite, right? If I need to move it left, I got to add the number. If I have to move a graph right, I have to subtract it. Phase shifts are always opposite, okay? So I need to add this to my phase shift. Well, that means that my new equation, let's call this big H of t, it's going to be, all I got to do is take my original equation here and just add 2.7 to it. So it'll be 10 cosine of 5 pi ninths, parentheses, now t, and what are we doing, Brady? Adding or subtracting that number if I want to move it left? Adding it, 2.757. Now I realize that's a truncated number. If I really wanted to, I could store that and use the stored value in my equation, but go ahead and write it out and then plus 50. Okay, now if your equation had been t minus 0.9, guess what you do? You would write t minus 0.9 plus 2.757, and then you would just combine those two numbers. Does that make sense? So it doesn't matter what the equation was originally, you just add 2.757 and you get your new equation. So that's what's nice about having the original one being centered at 0. And now the last thing I'm going to do is I'm going to verify that. I'm going to go to y equals. I'm going to get rid of this. And I'm going to come up here and I'm going to type in my brand new equation just to make sure. So I'm going to come over here and I'm going to put parentheses x plus 2.757 close plus 50. And now when I hit graph, you're going to get the same oscillating sinusoidal graph. But now when you hit trace and punch in a 0, boom, what does it tell you? What's the y value? At 0 now, when he started his stopwatch, it's at 50.9999999, which is 51, right? How come it doesn't say 51? We round it with 2.756, but that gives us confirmation. And is it going up or down at that point? It's going up away from the floor, which is what we want. If you graph this and you see that it's going down, that means you did the wrong thing. You subtracted instead of added. All right, so we're not going to yell at the little sister. She was excited, right? It's kind of flattering. She was impressed with our handiwork. She wanted to play with the toy. No worries. We got this, little sis. We'll just adjust our equation. All right. And that's it. Y'all can handle that, right? Of course you can. All right, tomorrow we'll do the Bay of Fundy problem, which is it's fun. Try to say fundy without saying fun, right? Can't. All right. Yeah. Anyway, and then we'll test on Monday. Questions, comments? I was going to give you the rest of the class to work in your worksheet, but there's only like 3 minutes left. So I guess we can still say the rest of the time to work on it. Okay, arrivederci. Enjoy the rest of your National Tater Day. You can celebrate by throwing taters off the top of the Eiffel Tower, right? Because it's also Eiffel Tower.